So good afternoon to all of you. So we earlier we discussed the subspace topology, and then we have seen that a subset of the subspace is closed if and only if it is of the form C intersection Y, where C is the closed subset of X. So this is one of the result in the subspace topology. And we discussed the interior and closure of a set. So interior of a set is if A is a subset of X, then interior of A is defined as union of the open sets which containing A, and closure of A is defined as the intersection of all closed sets which containing A. So we have seen that one result regarding the closure with respect to subspace, that Y is a subspace of X and A is a subset of Y, then a closure in Y is equal to closure of A in X intersection Y. And we discussed some example also of this type, and we have seen some of the example of closed subset of Y. So in the previous lecture, we revised all these things, and then we discuss one result. Yeah, so we discussed that A and B are the sets. A and B intersect if A intersection B is non-empty, and A does not intersect B means A and B are disjoint sets. And using this terminology, we proved a result that says that A is a subset of a topological space X, then small x belongs to a closure if and only if every open set containing X intersects A. And we also proved that this is equivalent to the condition that every basic open set containing X intersects A. So if you recall that what is meaning of basic open set if I take the topology called space to be R, and if I take the usual topology, standard topology on R, then basic open set is nothing but interval. And on the other hand, if I take X to be the R2 and I take standard topology, then basic open set is nothing but the open disk. So that way you can compare this result with result in analysis 1, that X belongs to A closure if and only if every neighborhood containing X intersects A. Right. So now neighborhood means either a open disk or open interval. But on the other hand, these two conditions are equivalent. So therefore, instead of considering basis element as neighborhood, we can also consider open set as a neighborhood. So in topology, we are not considering basic elements as a neighborhood word, but we are considering the general concept, which is open set containing the point X as a neighborhood of X. So that is the starting point for today lecture. So this result we proved in last lecture. Now let us start the today lecture. So first is the definition of neighborhood. We say that U is a neighborhood of point X if X belongs to U and U belongs to tau X. So basically U is the open set containing X. Then we say that U is a neighborhood of X. So neighborhood depends on the open set and open set depends on which topology we are considering. So now we have the notion of neighborhood. Neighborhood means the open set containing the given point. So once we have neighborhood, we can discuss limit points. So what is the definition? So if you recall the definition of limit point from real analysis, then X is a limit point of A if every neighborhood intersects with the set in the point other than the point itself. So let A is a subset of X and here what is X? X is a topological space. We say that X is the limit point of the set X if every neighborhood so neighborhood means open set here of X intersects the set in a point other than X itself. So X itself means other than the point X. So note that limit points are also known as cluster points and accumulation points. So these two are the same terminology, that the point is cluster point means the point is limit point of that set. So whatever condition is given here, that every neighborhood intersects A in a point other than X, that is same as X is a limit point of A if every open set U containing X intersects A in a point other than X. So that means it intersects A minus X basically. And this means that X is a limit point of A if X belongs to A minus X closure. So if you recall the result that X belongs to some set and the closure of some set if and only if every open set containing X intersects that set. So therefore these two conditions are equivalent. And this is the definition of limit point. So this is a if and only if statement, right? So this is just a mathematical meaning of the limit point we have written here, but the definition says in terms of the closure of set. So let us go to the theorem. So from real analysis we know that A closure is equal to A union the set of all limit points. So that we want to prove in the topological space setup. So let X be a topological space and take any subset of X. So let us pick some notation for the limit point. So let A dash be the set of all limit points of the set A. Then what we want to prove? We want to prove that A closure equals to A union A dash. So that is what we want to prove, and this already we know from real analysis, but we want to prove in the general setup of the topological species. So since these two are the sets and we want to prove they are equal, we first prove that the first set is contained in other set, and then we'll prove the second set is contained in the first set. So let us prove the easy part. If I take X belongs to A dash, that means X is a limit point. So X is a limit point, then what I will get? I will get X in the A minus X closure. And then we know that X minus A closure is a subset of A closure. So therefore we get X is in the A closure. So we proved that A dash is a subset of A closure. So what I want to prove? I want to prove this is a subset of this. So first I prove A dash is subset of A closure, and we already know that every set is subset of its closure, right? Because closure is the intersection of all closed sets containing A. So it by default contains A by the definition of closure. So altogether we will get A union A dash is a subset of A closure. So one way we have shown that A union A dash is contained in A closure. Now this converse part, that is also simple. So conversely, we want to prove that we start with X is in A closure, and then we have to show X is in A union A dash. So what we want to prove? We want to prove X is in A union A dash. So clearly, if X belongs to A, we started with X belongs to A closure. So if X belongs to A, then obviously X is in A union A closure, and in this case we are done, right? If X is in A, we are done. On the other hand, suppose X is not in A, because for every set A there is only two possibilities: either X belongs to that set or X does not belong to that set. So on the other hand, if X is not in A, then if I want to show X belongs to A union A dash, then I have to show that X is in A dash, right? So now we know that the second case is X is not in A, and we want to prove that X belongs to A dash. So again we will use the result of X belongs to A closure. So since X is in A closure, every neighborhood U of X, so neighborhood means open set, every open set U of X intersects with A. So what is my goal? I want to prove that X is in A dash, and to prove X is in A dash, I have to show that every neighborhood intersects with A other than the point X. So I know every neighborhood of X intersects with A, and I know X is not in A. So this both facts will give me along with X does not belongs to A, we get that every neighborhood U of X intersects with A in a point other than X. So what we have proved is that basically we have a set A, and so A is kind of in the points inside this circle, and I have a point X which is not in this open disk. So X will be kind of in A closure, but it is not in the set, right? So if I take any neighborhood around kind of X, then it will always intersect A in a point other than X. That is what we are doing here directly without considering any particular set A. So therefore what we'll get is X is in A dash. So this will complete the second part. So only thing here we are using is the result that X is in A closure, means every open set intersects with A, and since X is not in A, it will obviously intersect in a point which is other than X itself. So this is just simple result which we have proved in terms of limit points. So such a result we already know from real analysis, and examples you know from real analysis. So I don't want to take any kind of other example, any specific which is other than real analysis. So this is what regarding the limit points. So any doubts so far in the proof of this result? Any doubt? Okay, so if there is no doubt, then let me continue with the next terminology, that is a Hausdorff space. So I will discuss some example of Hausdorff space. And then we'll prove one result. So a topological space X is called a Hausdorff space if it satisfies the property that for each distinct points x1 and x2 of X there exist neighborhoods u1 and u2 of x1 and x2 respectively, that are disjoint. So what is neighborhood? Neighborhood means what?
Open set.
Open set, right? So in topological space, neighborhood means open set. So we know topology means we know the elements of the topology, and we know that elements of the topology are open sets. So elements of tau are open sets. So what is meaning here is that, so let us see the example. So if I take x equal to R2 with the standard topology, then let us check whether this is a satisfies this property or not. The question is R2 with respect to the standard topology is Hausdorff or not. So to check it is Hausdorff or not, what we need to do, so basically you are taking R2, x equal to R2. So basically it is xy plane, and then I'm taking 2 points x1 and x2, which are distinct points in R2. So it has two coordinates basically. So is it true that I can always find two open sets, one which contains x1 and one contains x2, and these two open sets are disjoint?
Yes, sir, possible.
So how we will do, what open set we will take?
Any text we can take rectangular or circular.
Yeah, so rectangular region or circular region. So basically we can take the disk. So basic open sets we can take. So this is a B1. So it is a disk which contains X. Similarly, we can take other disk B2 which contains X2. So it is not necessarily that X1 and X2 are center of those disks, but we need two open sets which contains x1 and x2, and the intersection of those open sets should be the null set. So this is possible in R2, so therefore R2 is a Hausdorff space. So in fact here you can find the radius also by looking at the distance between x1 and x2, and then you take the radius half, and in fact you take the disk around x1 with the half distance of x1 and x2. That will work. One disk around center with x1, one disk around center with x2. So this is a Hausdorff space. Let us discuss a space which is not Hausdorff. So let x to be R with finite complement topology. So question is whether this is a Hausdorff or not. So I have already mentioned that I will show that this is not Hausdorff. So suppose I want to check whether it is Hausdorff or not. So I have to fix some 2 points. So for simplicity, let us take whatever point you can take, but for simplicity, I'm taking let 1 and 2. So basically what I'm taking is let x1 is 1 and x2 is 2. So clearly x1 and x2 are disjoint points in R. So what I want to show is I want to show that can I find two open sets in this topology such that the two open sets, one containing 1, other containing the point 2, and they are disjoint. So let us suppose there are two sets, two such sets. So let U1 contains 1 and let U2 contains the point 2, and U1 and U2 are open in cofinite topology. So what is meaning of that? U1 and U2 are open means
Means their complement is either finite or entire
either finite or the whole
R.
set R, right? So therefore U1 complement is finite uh, and U2 complement is either a finite set or the whole R. So now what can I say about U1 intersection U2? So I'm saying is a finite set. Is it possible?
Yeah sir, when its complement is R होगा तब even to 5 हो तब हो सकता है सर, otherwise नहीं होगा.
So can a set has a complement R and it contains some point?
Sorry. Yeah.
So that is not possible, right? So basically, since U1 and U2 contains a point, the second possibility we will not have, because otherwise, if the complement is R, then the set is null set. So it cannot contain 1 or 2. The only possibility is the U1 complement is a finite set. So let, for example, U1 complement is A, U2 complement is B, and A and B are finite set. So in this case, what will be this intersection? So this intersection will equal to the B complement. It will be equal to A union B complement, right? This is A complement. U1 is A complement, and U2 is B complement. So A complement intersection B complement is A union B complement, and this is the infinite set, because when you remove A union B is a finite set because A and B are finite, and when you remove a finite set from R, you will get infinite set. So therefore, this is not a finite set.
So sir, is it possible to make choose that kind of even that their complement is finite other than 5?
Obviously, you just take one complement. U1 is one complement. Sorry, U1 is two complement, and U2 you can take, for example, the set which is one complement. So this is the specific choice of u1 and u2. You can take, for example, 2 comma 3 complement also as u1. Right?
Okay.
So these are just simple example which we have discussed that this is not a Hausdorff space. This topological space is not a Hausdorff space. So just to give you example that there are certain examples which are topological space but they are not Hausdorff. So now let us see one simple result regarding Hausdorff space. We know that every finite subset of real line is closed. Every finite subset of R is closed in R. So the same property holds for the Hausdorff space also. So if I have a Hausdorff space, then I can prove that every finite subset of that space is closed. So let us try to prove this. So what is the Hausdorff space? I have 2 points distinct. I can find 2 open set containing those points which are disjoint. So we know only this property about this space, and we want to prove that every finite subset of that space is closed. So since this is a topological space, since X is a topological space, and in a topological space, what we remember is every finite union of closed sets is closed. So if I can prove that singleton is closed, then I can prove using this result that every finite set is closed, because finite union of closed set is closed. So therefore it is enough to prove that finite union of it is enough to prove that singleton is closed. In the Hausdorff space. So this is our claim. So what is the claim? claim is that singleton, suppose x naught is element of x, then we want to show that x naught is closed in the Hausdorff space. So what is the definition of Hausdorff space? Hausdorff space is that if I have two distinct points, then I can find two neighborhoods. So now I know one point, which is x naught. So to find another point, what I will take? I will take complement of this set, right? So let a point x, which is not in x naught. So basically, x is in the complement. So it is not mentioned here, but basically x contains at least 2 points, and if x does not contain 2 points, then by trivially it satisfies this property that it is Hausdorff, and in that case x is either phi or singleton, so therefore it is every subset is closed. So anyway, just forget that. So let x is any point which is not in x naught. So then what we'll get? We get basically 2 points which are not same. So using the definition of Hausdorff space, we will get two neighborhoods ux and ux naught, such that x belongs to ux, x naught is in the open set ux naught, and this open sets has a disjoint. They are the disjoint sets. So what we are getting is basically we have x and x naught. So we are getting two neighborhoods which are disjoint. So this is basically Venn diagram. We are not in R2. So now what can we say? Because we know ux intersection ux naught is not phi. That means what? That means, and x naught belongs to ux naught. So basically we know that ux cannot contain the point x naught, right? Because ux intersection ux naught is null set and ux naught contains x naught. Therefore ux cannot contain the point x naught. So what we get is x belongs to ux, and which is in the complement of x naught, right? Because x naught cannot be in this set and ux contains x. So I have a neighborhood which basically does not intersect this set. So there is a neighborhood which does not intersect this set. So that means X cannot be inside X naught closure. So here we are taking A is singleton X naught. So we know that X is not in A closure if and only if there exists U such that X belongs to U and U does not intersect with A. So that is this neighborhood. U is Ux for this example, right? So X does not belongs to A closure. That means X is not in X naught closure. So we proved this X is not in A closure, X naught closure from the fact that X is not in X naught. So if X is not in X naught, X is not in X naught closure. So that will give us the contrapositive will give us X naught closure is a subset of X naught. And on the other hand, we already know that the set is always contained in its closure, right? So therefore, using these two facts, we get X naught closure is X naught itself. And if I have a set whose closure is the same set, that means the set is closed. So this will prove our result that if I have a Hausdorff space, I can find two neighborhoods and using that two neighborhood condition and using this property of the element does not belongs to the closure, we will get that X naught contains its closure and therefore the singleton X naught is the closed set. So what we proved is every Hausdorff space in every Hausdorff space finite set is always closed. But converse is not true. So what is the converse? Converse is that if I have a topological space in which every subspace is every subset is closed, then whether it is Hausdorff or not. So converse is not true. We have already discussed one example of this topological space, which is not Hausdorff. But you can see that every subset of R is closed here. So why every subset is closed here? Every finite subset is closed. Why? So we are discussing
Because finite.
we are discussing cofinite topology. So the open sets are complement of finite sets. So therefore all closed sets are nothing but the all finite sets here. Right. So by the definition of topology, all the closed sets are all the finite sets are closed in this topology. But we have discussed that this topology is not Hausdorff space. So therefore converse of this theorem is not true. So any question so far? I would like to stop here.
No, sir.